In the previous episode, we explored the general structure of black holes, how they form, and many other detailed aspects. As I mentioned before, this topic would be covered in 2 parts. Today, we're continuing with part 2, where we'll dive deeper into theoretical concepts and explore what someone might actually experience if they were to fall into a black hole. If you enjoy the video, don't forget to hit the like button, subscribe to support the channel, and share your ideas for future videos in the comments. Now, if you're ready, let's continue our journey into black holes right where we left off. Imagine that you are an astronaut sent on an extremely dangerous mission for the future of humanity. Your objective is to get as close as possible to a black hole and report your experiences in real time. What you go through during this mission could significantly advance humanity's understanding of space and improve our technological capabilities. To understand the physical processes experienced by an observer approaching a black hole, we must first fully grasp the nature of gravity, as described by the famous general theory of relativity. According to this theory, mass bends the fabric of space-time, and this curvature determines how objects move. Black holes represent the extreme limit of this curvature. Therefore, approaching a black hole is not just entering a strong gravitational field, it is entering a region where the familiar behavior of space and time completely breaks down. The most critical boundary surrounding a black hole, as we discussed in the previous video, is the event horizon. This boundary represents the point where the escape velocity reaches the speed of light, meaning that nothing, not even light, can escape once it crosses this limit. In other words, by accepting this mission, you are also accepting that there is no return. For an external observer, an object approaching a black hole never appears to fully cross the event horizon. This is mainly because the intense gravitational field lowers the frequency of light and slows down the flow of time. The light emitted by the object shifts to longer wavelengths and eventually becomes invisible due to gravitational redshift. At the same time, due to time dilation, the object appears to slow down more and more from the perspective of the outside observer. This phenomenon is one of the strongest pieces of evidence showing that time is not absolute, but depends on the observer's frame of reference. However, from the perspective of the person falling into the black hole, time continues to flow normally. The observer crosses the event horizon within a finite amount of time and does not feel any physical barrier or wall during this transition. This shows that the event horizon is not a locally special point, but rather a globally defined boundary. Another extremely important effect experienced while approaching a black hole is tidal forces. Because the gravitational field is not uniform, there is a significant difference in the force acting on the part of the object closer to the black hole compared to the part farther away. This difference causes the object to stretch along one axis while being compressed along the perpendicular axis. This process is known as spaghettification, a term many of you have probably heard before. It becomes extremely destructive, especially in smaller black holes, even before reaching the event horizon. In supermassive black holes, this effect may be weaker at the event horizon, but it inevitably becomes extreme as you move deeper inside. This demonstrates that black holes are capable of disrupting not only macroscopic structures, but also matter at the atomic and even subatomic level. Once you cross beyond the event horizon, the roles of space and time coordinates, so to speak, begin to switch. In the external universe, time always flows forward, while movement through space in different directions is possible. However, inside the event horizon, all possible future paths inevitably lead toward the singularity. For this reason, reaching the singularity is not a matter of choice, but rather a necessary consequence of the causal structure of space-time. The singularity is defined as a region where density becomes infinite and the curvature of space-time becomes undefined. However, the term infinity here does not necessarily mean that a physical quantity is truly infinite, but rather indicates that our current theories break down at this point. Both general relativity and quantum mechanics cease to function together at the scale of the singularity. This demonstrates that modern physics is still incomplete and that a more comprehensive theory, such as quantum gravity, is required. It is also well known that black holes are not merely structures that consume matter, but they also bring along profound problems related to energy and information. The process known as Hawking radiation arises from applying quantum field theory in a black hole background and shows that black holes are not completely black. Near the event horizon, virtual particle pairs are formed. One falls into the black hole while the other escapes, and this process is perceived as radiation by an external observer. This mechanism suggests that black holes can lose mass over time and eventually evaporate. state. However, this leads to a serious theoretical issue known as the information paradox. If a black hole completely evaporates, what happens to the information of the matter that fell into it? This problem is one of the most puzzling questions in modern physics. According to quantum mechanics, information cannot be destroyed, yet black hole evaporation appears to imply that information is lost. This contradiction has become one of the most active areas of research in theoretical physics, and approaches such as the holographic principle attempt to resolve it. Recent studies on black holes also indicate that space-time is not merely a passive stage, but rather a dynamic and interactive structure. In this context, another theoretical construct emerges: wormholes, also known as Einstein-Rosen bridges. These structures are mathematical solutions that connect two different points in space-time through a shortcut. However, for such structures to remain stable, they require exotic matter with negative energy density, which has not yet been observed. Of course, this does not mean it will never be observed. Therefore, while wormholes are theoretically possible, their physical existence remains uncertain. As we approach the limits of black holes, all existing physical theories become insufficient, and scientists are inevitably forced to turn toward more speculative yet mathematically inspired models. Every phenomenon that cannot be explained within the classical framework points to the existence of a deeper theory. At this stage, black holes cease to be merely astrophysical objects and instead move to the very center of questions about the fundamental nature of the universe. The uncertainties that arise in the region of the singularity lead us to question the continuity of space-time itself, paving the way for the development of quantum gravity approaches. One of the most striking ideas developed in this context is the notion that black holes may not be endpoints of our universe, but rather gateways to other universes. Within the framework of the multiverse theory, this approach suggests that our universe may not be a single, isolated structure, but instead part of a much larger cosmic system. According to this model, the singularity formed inside a black hole could represent a new beginning point for another universe. At this point, we encounter a concept that has also been discussed previously on this channel: white holes. In simple terms, white holes can be considered the exact opposite of black holes. Just as nothing can escape once it passes through the event horizon of a black hole, nothing can enter a white hole. Instead, a white hole repels everything that attempts to approach it. Some theories present fascinating possibilities in this regard. According to certain models, matter entering a black hole could eventually be expelled from a white hole at another point in space. Of course, this varies depending on the theory. Some suggest that black holes and white holes exist within the same universe but are extremely far apart, while others propose that they exist in entirely different universes, meaning that matter entering a black hole could be ejected into a completely different universe. From this point onward, almost everything said about black holes becomes highly theoretical. While many of the concepts discussed so far are also based on theories and models, they are grounded in strong mathematical foundations and are considered highly probable within the framework of known physical laws. However, beyond this stage, many theories are no longer strictly based on mathematics and often venture into the limits of human imagination. Of course, this does not necessarily mean that all such theories are incorrect. For example, wormholes are mathematically required to exist, yet they have never been physically observed. Even if they have not been directly seen, the phenomena they would create in their surroundings could potentially reveal their presence. Unfortunately, no such evidence has been found so far. At this stage, white holes, although still purely theoretical, are considered a plausible possibility. This is because what we refer to as wormholes may indeed be the connection between black holes and white holes. Hopefully, these theories can be proven within our lifetime, allowing us to finally answer many of the questions we are curious about. Our technology and our ability to observe the universe continue to improve every year. In particular, the James Webb Space Telescope has provided us with a tremendous amount of new data and insight. Thanks to it, we have been able to observe many phenomena that were previously beyond our reach. In conclusion, what lies beyond black holes opens the door not only to the observable universe, but also to all theoretically possible realities. At this point, we must draw not only from science, but also from disciplines such as philosophy. Compared to the previous part, this documentary focuses more on theories, including models that may not have a strict mathematical foundation, but still hold the possibility of being real. Although science enthusiasts like myself prefer to remain within the boundaries of established science, when it comes to mysterious objects like black holes, we are sometimes compelled to explore these speculative paths. I hope you enjoyed this video and had a great time. Unfortunately, that's all for today. If you liked the video, don't forget to hit the like button, subscribe to support the channel, and share your ideas for new videos in the comments. See you in the next video. Take care and goodbye.